Hello everyone, after the last video this one is about much happier news and will be one of many additions to the explanations on thrusters and electric thrusters that I have made before, as there are really quite a few oddly specific outlandish thruster concepts and also quite a few developments on new thruster concepts that are actually being tested and developed right now. So today I'll give a very quick explanation and summary on the new developments at ESA, the European Space Agency, and their air-breathing electric thruster for satellites. First of all, a short announcement. The next important live events that I will stream will be on March 21st. One of them a manned Soyuz launch to the International Space Station at around 17:45 GMT, which I will live stream, as well as the docking to the International Space Station, and as always there are astronauts on board, so it might to some be a bit more interesting than the usual satellite launches. Then 4 hours later an Ariane 5 will launch with 2 communication satellites. That will be the first Ariane 5 launch since the partial failure in the last launch, so it's also kind of interesting, and there might be more information as to how exactly they addressed the issue. Now to ESA's air-breathing ion thruster. That is the first time that someone has managed to develop an air-breathing thruster that operates at orbital speeds. Now it's hard to actually call it air-breathing, of course there's semantics involved. Is this really air? It's basically the thin gases at the very upper levels of our atmosphere, and it's important to keep in mind that very low Earth orbit satellites are still within the uppermost incredibly thin parts of the atmosphere. It basically exponentially declines, so it never really cuts off, and the ISS, for example, is slowly slowed down by this and needs to be boosted up regularly to stay in orbit. Now this isn't really a notable slowdown, but still for a very long time you'll eventually have to boost up again, and low Earth orbit satellites need quite a bit of fuel for this, in addition to the fuel you already need for some orbital maneuvers and adjustments, so their lifetime is currently very limited. Now in general, for orbital maneuvering, ion thrusters or other electric thrusters are a good choice because you don't need much thrust, but you do need a lot of delta V. You don't need much thrust because you only want tiny impulses over months that you can correct small problems or do small adjustments. But since this adds up over years and years, you still need quite a bit of delta V, and you don't want to carry heavy fuel with you, so a high specific impulse is important. And of course electric thrusters can provide this, where the energy is not stored in the actual fuel but comes electrically from the outside. The energy is delivered via a solar panel, which if you have a lot of time can deliver any amount of energy if you wait long enough. And so you can ramp up the speed at which your fuel or your propellant leaves the thruster, especially using ion engine, to some ludicrous speeds, which means that you don't need much propellant for your thrust, so you can work very fuel efficiently, but of course you need more energy, because energy is essentially speed times force or speed times thrust. So the faster you eject your propellant, the more energy you need per thrust, which is why you can't really do that with chemical engines, because there's not really any fuel that would store that much chemical energy per fuel unit that it would eject that fast. And it's also why you can only maneuver very slowly with this, because you need a very power source for anything more, and there aren't that many choices for power sources in space. You can really only go for solar panels or small nuclear batteries, neither of which would usually provide much more than some 50 watts per kilogram on average. So you're very much limited to something like 1/1000th of a g of acceleration, and that's kind of important to understand, because it often annoys me when you read things like this new ion thruster could bring us to Mars in 2 weeks or something like that. The people don't really see the entire system optimization or the actual limitations behind this. Like, for once, it's not really usually the thruster that limits you, but the energy source, and of course chemical rockets can bring you anywhere at any speed if you bring an exponentially insane amount of fuel with you. Now this thruster goes essentially one step further by completely removing any propellant tanks, because it uses the propellant from the atmosphere. letting in air or gas through what's basically an air intake and accelerating that and using Newton's third law on that to produce thrust rather than a gas that you store in a tank and eject. The working principle is the same as with an ion thruster. You heat up and ionize the gas, then use an electric field to accelerate it, except that you have much less control over what kind of gas you get and under which condition. The advantage is of course that if you use this as a propellant source and solar panels as a power source, you're not really using anything up at all, and so your satellite, if it's very well built, could hypothetically stay up indefinitely. You basically have an infinite reserve of delta V for very slow orbital maneuvers, adjustments and boosts as long as you stay in this very upper atmosphere in low orbit, which is quite interesting since low Earth orbit is now getting more and more interesting for communication satellites since they have much less lag, and also other Earth-bound satellite applications like mapping and observation. And it's of course interesting what might happen with this technology in the future if it is further developed. We might of course hypothetically be seeing the very first theoretical steps toward the ramjet concepts for interstellar engines here, although that is very far out and hypothetical. But in the relatively near future, what this might mean is that satellites can maneuver to quite an unprecedented extent as long as they stay in low Earth orbit, which of course is already becoming a lot more attractive since you are no longer limited by aerodynamic forces. You're not being slowed down until you eventually fall down, but you can keep yourself up indefinitely. And in addition, you can change your orbit, which might have a lot of unforeseen consequences that I can only speculate over, and I might make a longer video about these consequences in specific. But for example, maneuvers like orbital inclination or plane changes have always been rather annoying and need a lot of delta V, but with this kind of technology you could hypothetically launch a satellite from a launch site that is not at the equator into an, say, almost polar orbit, and then slowly over time adjust it step by step towards an equatorial orbit or the other way round, which would of course take years, but at least it's possible and it might bring some interesting possibilities with it. Now there isn't much in terms of specifications released yet, and in fact this is far from a final thruster. Of course the media is quick to report about this, but it's really a very early experiment. A pre-existing basic ion thruster was essentially disconnected from its xenon tank, slightly modified, put together with an air intake and put in a particle generator, or what's essentially a incredible high-speed, low-density wind tunnel. And it was shown that it's possible for that ion thruster to create more thrust than the air intake creates drag, to accelerate these ions, which are no longer xenon ions but rather mostly nitrogen ions, to a speed beyond their intake speed, beyond orbital speed, and create useful thrust. So another thing that's interesting to look out for in the future is where this technology actually goes in terms of development, and what kinds of specifications an ion thruster designed specifically for this purpose might have. Of course you have to stay faster than the intake speed, but unlike with earlier ion thrusters, there's no longer really a need to go for incredibly high exhaust velocities, which means that you can go a lot more energy efficient and can do a lot more with your limited energy supply, which might also make other types of electric thrusters interesting again, like arc jets or resistor heating jets, although those usually need higher density of fuel. The other great advantage of ion thrusters besides the exhaust velocity is that they don't really need dense fuel at all. They really work on each atom individually, and if you have several atoms of fuel, which you usually have, it still works on each in parallel, but it doesn't require an actual pressurized gas to work, whereas arc jets still work by pressure and a nozzle, which means you actually need a significant density of gas for them to work. But of course ion thrusters also have an advantage of simplicity while also being complex. They are complex to design and simulate and develop, but once they are built, the actual technology is relatively simple. You need a sort of high voltage generator or high voltage step up or transformer, but once you have that, The thruster itself is mostly rigid parts. There's no moving parts, no gas dynamics, no nozzle. You essentially have two grids of metal that are under high voltage, and that's it. So they might also develop the necessary longevity to actually take advantage of that hypothetically indefinite stay in orbit, and you could see satellites with a much longer lifetime being built in the future. So this was just a very simple first look at the news of an air-breathing ion thruster and what that might actually mean. I will make a more in-depth explanation if we get more details on its actual design. If you have any questions about spaceflight or the underlying physics, I'm always open for requests, and as always, thanks for watching.